First, let me introduce myself. My name is Pedro. I'm 34 years old. I'm Portuguese. I can be found online generally by PMMAGA. Now the clicker worked. A little bit delayed. I work as a DevOps at a Dutch company called Emesa, and I work from here, from Portugal. I'm generally an open source enthusiast. I contribute to PHP core, but I'm not going to talk about PHP. Yay! And I'm a member of Defesa dos Direitos Digitais, which is a Portuguese association to defend your digital rights. And I wrote my own tiny container runtime to understand a little bit better how containers worked in PHP. But okay. We are going to talk about containers, how they came about and how do they work. And this is, yeah. Containers basically offer a way to... Why you do this to me? Okay, containers offer a way to isolate your process or your application from the rest of the system without... maybe someone else is clicking my... Maybe someone else is trying to change their slides and they are changing mine. This is pretty amazing. I don't know. Okay, or maybe I just disconnect this one. And now I should be safe. Okay. Yeah, so they offer a way to isolate a process or an application from the rest of your system without the overhead that typically comes with doing that with a virtual machine. And so to talk a little bit about the history and how they came to be, it all started around 1979. I wasn't born yet, where they introduced Shroot. And so Shroot basically is a tool that is offered on any Linux system that allows you to change the root of the file system that is visible for that process. So from the perspective of that process, if we are here and we shroot to this folder, from that moment on, this process only sees root as this folder, and it's not, well, if you really try hard, you can get away from it, but in theory, this is everything that you should be able to see. So this is one of the things that already provides some isolation for the file system from the perspective of a process. Then, 21 years later, not much happened in this space for a while, but in the year 2000 we got FreeBSD jails, which offered already a little bit more of isolation, other than just shrooting. And they already allowed, for instance, to assign a different IP per container. So this was kind of something new, and it was invented by some guys that were running a hosting company, and to try to cut costs, let's put everything in the same machine, let's try to reuse as much as possible, but still assign different IPs to the different clients, customers. Then, in 2001, Linux vServer came to be, which was pretty similar to FreeBSD jails. It offered also some degree of isolation, but it needed a patched kernel, so it couldn't work just on top of normal Linux kernel. It needed a patched version to do its thing. Then, in 2002, we got Mount namespaces, and we are going to talk a lot about namespaces a little bit later, but basically this was the first namespace that was available in the kernel that could isolate the mount space, I'll talk about it later, from the rest of the system. Then, in 2004, we got Solaris containers, which were containers at the Solaris version of these containers, and allowed also to control the resources that were available, defining different zones in your system to run different things with different amounts of resources. In 2005, we got OpenVZ, which provided isolation and also checkpointing. So it was, as far as I know, it was the first system that allowed you to take a checkpoint of your container at that point in time so that you could easily come back to it. But it also needed a patched kernel, so it was not just plug and play. You needed to have this patched kernel. And in 2006, we had process containers, which was developed at Google. And it was created to limit and account for the resource usage of your containers, or sorry, of your processes. and it was later merged into the kernel of Linux in 2008 as C groups. So when you see C groups on a Linux system, it was actually the process containers that were created by Google back in 2006. And they changed the name to C groups also to avoid a little bit confusions between containers and not so much containers. Then, in 2008, we got LXC. LXC stands for Linux Containers. It makes use of C groups and the kernel namespaces to achieve this isolation. It contributes back to the kernel with user namespaces. So they were the ones that implemented user namespaces and made that available in the kernel. It was the first one that actually worked fully on an unpatched kernel, so you didn't need to modify your kernel to get LXC to work on your system. It is currently maintained by Canonical, so Canonical kind of adopted the project and it's now developed there. And it is used typically for system containers. And speaking of system containers, just to make a distinction, system containers are containers that typically run an entire system, as opposed to an application container that only runs one application or even one process if we go to that level, but it can run multiple processes, but it's typically just to run one application. System containers, on the other hand, typically the first process that runs inside, it's actually init, so they actually run an entire operating system on top of the kernel of the host, but they actually run an entire operating system on a container. And this is what is pretty different from the application containers. And yeah, they have different uses. System containers are more akin to a virtual machine because you have a full-on operating system, and application containers, well, it's just for an application. So, continuing it a little bit with the history. In 2011, we had Warden, which was implemented by Cloud Foundry. It used LXC as a base runtime initially. Eventually, they also got away from it, and now it's independent even from Linux, and it allows that type of containers to run on multiple operating systems. So it's no longer limited to Linux, it actually works on multiple operating systems. Then, in 2013, we got Let Me Contain That For You, developed by Google as well. It was, as far as I know as well, the first containers that were made for application containers. And the applications were actually aware that they were containerized, and it allowed them to create subcontainers and so on. And yeah, it was a little bit different from what we use now, but they allowed that. Eventually, it got abandoned in favor of contributing to libcontainer, which came from these very famous guys, Docker, which came in 2013. It was developed by .cloud, which later was renamed to Docker. It was very successful. Initially, it also used LXC as the base runtime, but later down the road, they actually ended up replacing LXC with their own lib container. And it introduced a lot of new things, including the layered images model that you are used to see. It made the container technology very popular, and most of us know about it today because of Docker. And it started also the Open Container Initiative, which develops the RunC runtime engine, which is actually the runtime engine of Docker. Docker actually runs on top of RunC, Docker containers. In 2014, we got Rocket, which was developed by CoreOS. It was also focused on application containers. It introduced the concept of pods, that some of you that are familiar with Kubernetes are also familiar with that concept. And it can also run containers based on Docker images. So you can use a Docker image, but use Rocket as its runtime. In 2016, surprise, Microsoft also did its thing. And now we have Windows containers, which started supporting running containers natively. Docker on Windows actually makes use of these, but as far as I know, as far as I understood, it still makes use of a thin layer of Hyper-V when you want to run Linux containers on a Windows machine. But recently, we started caring more about container orchestration than about the containers themselves. So Kubernetes is winning this race. And yeah, basically how you organize and manage your containers became more important than how you are running them. So the runtime is starting to be an implementation detail. People care more about how they orchestrate the containers than actually what system is allowing them to run on the lower level. And so probably if Kubernetes decided to change the runtime, they actually have that OCIR or no CRI layer that will allow them to switch runtimes very easily. And I guess that if they switch to Rocket at a certain point in time, most people wouldn't notice because the runtime of the container is starting to become just a very small implementation detail. But okay, so how do they work? So we're going to talk mostly about these three first things. So about root, how to isolate a file system, about the kernel namespaces, and about the C groups. And then, of course, that they have much more things going on. But, so root is what I said in the beginning. There is nothing else to add there. It's just for that process, from that point in time, you only see that part of the file system as being the root. You have no access to the rest of the file system. Then namespaces. Namespaces are really interesting. It's part of the kernel of Linux, and they allow, basically they provide the ways to isolate the rest of your system, not about file system, but the rest of the things. So to name a little bit the namespaces that are currently available, we have the mount namespace, which basically allows you to create new mounts on your file system that don't affect the host system. So you can mount something, you can mount a device, you can mount something different on a folder. If you are doing this inside the mount namespace, the host system cannot see that. So those mounts are only available for the process for the processes that are inside of this namespace. Then we have also the PID namespace. And the PID namespace is kind of similar to what we do with root, because the process will, from the process perspective, it will become process number one. And so if you think about the processes as a tree, right? All the processes are started by a previous process. When you start a new PID namespace, you're saying that the next time that you fork, next time that you start something, that new process will think that is process one. From his perspective, he's process one, and he cannot, because of this, he cannot refer to other processes in the system, because as far as it knows, he is process one, and he cannot see the rest. Then we have the network namespace, which basically just separates the entire network stack for that process. So not even local host will be resolved. You are very outside of the network stack that you have on your host. So, and yeah, if you do this, then you can create VETs, or you can create other ways to make your containers talk to each other, or things that are not talking about containers, just things that are running on different network namespaces. If you want them to talk to each other via network, you will have to create this network to allow them to talk to each other. And somewhat similarly, we also have the IPC namespace, which isolates the inter-process communication facilities. So the things that the ways that you normally have to have inter-process communication, if you start a new namespace for IPC, they will become not reachable. You cannot reach the host, and the host cannot reach the things that are running inside of this namespace. Other than this, we also have the UTS namespace, which allows you to change the host name that is viewed by the process. So your machine has a host name. You can start a new UTS namespace, and when you enter it, you can change the host name of the machine, because that will only be visible inside that namespace. So your host is not affected, only that the processes that run inside that namespace can see that change. We also have the user namespace, which isolates the users, the groups, and the privileges from the process perspective, and they typically have a mapping. So you can say that user 1000 on the host machine is user 0, root, inside that namespace. And so this is a way to have root privileges inside of that small container, inside of that namespace, but you are actually, from the perspective of the host system, you are still just user 1000, so you don't have any special capabilities. And then we also have the C group namespace, which basically, the C groups are also a hierarchy, and it also allows you to isolate the C groups from the rest of the system so that they cannot be viewed. And speaking of C groups, basically they allow you to impose resource limits to a process. So you can use C groups to say that all this process and all of its children are only going to have 10 megabytes of RAM available. And this is enough to impose that, basically. Okay, so let's do a little bit of some exercise, but actually I didn't think this through because I have one hand occupied with my microphone. Can I use this one? Is it possible? Yeah? Testing? Okay. Oh, I sound different. Okay. Okay, so let's yeah, try to emulate on the. Is this big enough? Can you guys see? Should I put it a little bit bigger? Yeah. So let's try to emulate a little bit a container runtime just from the shell. So to do this, I'm gonna start by getting an image from Docker. Okay, this is gonna fail. This is fine. I'll try again. I'll try again later. Yeah. Okay, so if we go now inside my Alpine folder, we can see that I have here the image, well, the whole 32717. And we are going to say that the root where we want to work is actually and that the working directory where we are and that we are also going to run yeah, good point. Okay, so we enter the namespace. If here so here we can already see that we actually have two shell, two SH processes running, and one of them is the one that we joined from here, and the other one was the original one. So basically, Docker exec in the end does something pretty similar. You also join the namespaces that your container is currently in, and then you can do whatever you want to do inside of that container. So yeah, actually just using unshare and nsenter, that are commands that are part of the Linux util packages, we can do already quite a lot. Okay. So back to the presentation. Thank you. Okay. But yeah, of course, that the runtimes that we are using nowadays are not only these. They have much more things. For instance, they also interact with AppArmor and the SL Linux to provide even extra isolation from the host system. They also do the entire network management for the containers and how they interact with the host and how they interact with the rest of the world. It does all the image management with the layers and everything like that. It does also the container management. And yeah, it has other things like the copy on write file system, the layered images, and all of that in the case of Docker. And then even more, like everything, lots of money, marketing departments, and things like that. And yeah, they just went with it, and it's brutal nowadays. They are everywhere. And yep, this is pretty much it. I don't know if anyone has any questions. Thank you. Any questions? Any takers? Maybe can we?
Does Kubernetes have a graphic interface?
So the question was if Kubernetes had a graphical interface. One of the things that you can install on Kubernetes and that you, well, typically would install is the Kubernetes dashboard, which is actually an application that runs on top of Kubernetes itself. So it's kind of like yeah, make your cake and eat it too. So they also use Kubernetes to deploy it. And basically then it's a web interface that on your browser you can visit it. And it has a lot of very interesting information about the things that are currently running on your system or on your cluster, basically. Yeah. Anyone else? No? Okay, then that's it.